So the people that are continuing to come in, they will have chosen lunch over WCF, which is always a bad choice. So thank you for attending today. This is the Zen of Windows Communication Foundation Performance and Scale. My name is Nicholas Allen, and for the next 45 minutes, I'll be talking to you about how to think about WCF. So what is a Zen talk? Because there's not a lot of talks that are titled Zen in the PDC topics. You see a lot of talks where they do coding and demos, but this is a talk about how to think about performance, how to think about building distributed applications using WCF. It doesn't mean that this is going to be an easy talk. There's going to be a lot of difficult concepts. We're going to do some deep dives into how WCF actually works into the covers. And I'm going to assume a little bit of background that you've got on WCF already. You should be very familiar about addresses, bindings, contracts, endpoints, building WCF services. What you don't need to know is anything about other Microsoft technologies. So I'm going to mention at times Windows Workflow Foundation, talk about some of the future of WCF. I'll talk about some new things coming like Dublin and Oslo. But wherever I talk about those things in this talk, I will give you all the context you need, or I will point you to the sessions where you can learn more. So yesterday we did a talk, Kenny Wolf did a lap around WF 4.0. You can go see the recordings of that. Ed Pinto tomorrow is going to give a talk about WCF 4.0 together with WF 4.0. I'll tell you how to think a little bit about WCF 4.0. Ed will show you how to actually use it. Tomorrow, Dan Eschner is going to tell you about Dublin. Dublin's extensions to the Windows Application Server role for hosting managed services. And we'll see how that comes in handy when we're building WCF services. And finally, I'm actually not going to say a thing about Oslo today. You've heard the keynote, Don Box talked earlier this morning. You're going to see more about Oslo throughout the day. So I recommend Doug Purdy's talk immediately after this session. So everyone go and see that. So here's how the talk's basically going to work. There are two parts of this talk. There's WCF today, and there's WCF in the future. In each part of the talk, I'll tell a story. And the story is just a guide that we go in order to lead us through all the different parts of WCF performance. And then I'll do a little bit more detail into the technology, doing the deep dives, and I'll spend most of my time on WCF performance today. I wanted you to kind of go out of this talk with practical things that you could use. We'll still talk about what's coming in WCF 4.0. We'll look at a little bit at the vision, but about 2/3 is going to be WCF today. So with that, let me tell my first story. And this is a story about a Formula One race. And you've heard a lot of analogies with Formula One and motorsports and those kinds of things for performance, but this is my Formula One story. So I was at the Formula One race in Indianapolis a couple years ago. And to date it, at the time, the champion Formula One racer was Michael Schumacher. And so if you've seen the races on TV, you just see a couple hours. But when you go to the races, it's actually a many-day event. And so you got to go things like, you see the amateurs run, you go to autograph sessions, and those types of things. And so I was at one of these autograph sessions. And there was this huge line waiting for autographs from Michael Schumacher and the Ferrari team. And I was just sitting there watching them. And one guy goes up to the front of the line and hands Michael this poster to sign. And he says, "No, I don't want you to sign it." And he tells the name of some other guy. And Michael Schumacher just looks at this guy like he's completely crazy. Guy repeats his request, and then Schumacher thinks about it and motions over to a track official. Track official goes down, and maybe 60 seconds later, you see a guy in Michael Schumacher's colors. And if you've seen those racetrack suits, they're not built for aesthetics. They're built for keeping you from not catching on fire. And this guy really filled out the suit. It looked like he enjoyed the beers when they went back to Germany. But the speed which he was running down the racetrack was rivaling the race cars. And it turns out when you're the assistant engine mechanic to the Ferrari team, and someone has snubbed the world championship race car driver to get your autograph, you don't take any chances that they may have run away. And the guy was nice enough to stay. He signed the autograph, and then he talked a little bit about what he did for performance in tuning engines. And I want to steal some of that material, just as kind of lessons that you can learn about performance going through WCF as a way to guide the talk. So the first lesson is more of a lesson about people. Performance is not a glamorous occupation. No one knows who Michael Schumacher's assistant engine mechanic is. Everyone knows who the race car driver is. But when you think about the performance of the system, if any little piece of the system is not performing up to par, then the driver has no chance of winning. And the same is true with performance in a distributed application. You may think that performance is, a lot of times less glamorous than building the features. It's not always the thing on the back of the box. But without crucial investments in performance, it's difficult for your applications to succeed. So with that, let's go into kind of more of the technology lessons about performance. So one of the things that we talked about when we were talking about building engines was understanding how the entire system works. So when they go off to build an engine, they get all the individual components, and they test and they performance tune the individual components as they go along. And then they assemble the engine together. And they find out that no matter how much performance tuning they do on the individual components, the performance of the engine when it's assembled is completely different, so they have to retune all the things. Then they put the engine in the car, and now everything's different again, so they're retuning again. And then they put the driver in the car, and it's all different. And it's because everything in the world is interconnected. When I build distributed systems, I'm going to be building systems that have a lot of different processes that are running at the same time. I'm going to build processes that go across a variety of networks, a variety of systems. And you can only understand how the system performs if you think about the system as a whole. And there's two key aspects of that. One is that somewhere in your system, when you're looking for a performance problem, there's going to be the rate limiting step. There's a step that tells you, this is the slowest step, and I need to find that in order to fix my performance problem. And there's two ways that rate limiting step could appear. One is that it's actually something that just takes a long time, and those are typically the performance problems that are easier to find. The other is that I've got some resource, and that resource can only be used in a limited variety of situations. For instance, I've got a computing resource where I've got only so much computing power, but I've got it all throughout the day. And so the other reason why a step might be slow is because I'm using my resources inefficiently. And those are the two key aspects to understand. We'll see how those kind of reappear throughout the talk. The second important lesson that we got from that was that when I think about the performance of my system, there is a certain design element that went into designing how the distributed system worked, how it coordinates, how it interacts with the other parts. And I can never beat the performance that is dictated by that base design. I'm not going to initially achieve the best possible performance for my design, and so I'm going to have to do some amount of performance tuning to even get close. But I'll never beat my design. So at some point, it'll always be the case where I have to stop tuning and think about my design in order to figure out how can I make the system better. The way that we do performance tuning in WCF is that you've seen a variety of knobs. If you've seen the WCF documentation, you might have seen that there is not just a variety of knobs, but say 2,000 or 3,000 knobs on all the different bindings and all the different settings that you can configure. And these knobs are very powerful in terms of controlling the performance of your system. And we'll spend a lot of time talking about how to understand and think about these knobs in order to achieve maximum performance in WCF. The downside of these knobs is that if you read the documentation, you can't really predict what's going to happen when you turn the knob up or down. And that's the key thing that I want to address in the talk today. The final thing we learned from systems is that the only thing that matters in performance is the actual measurements. I can't performance tune a piece of paper. I have to make certain assumptions about the world, but then I'll actually go make hypothesis about the performance of my system, test those assumptions. And it's only when I have the actual system in front of me, when I'm actually playing with the bits, playing with the system, that I can find out how I'm doing in terms of performance. And it's always going to be the case that reality makes a difference. It matters how the exact messages that I send, what they look like, their XML structure. It matters, what network I'm running on. In the WCF Performance Lab, we've got a whole bunch of people that work on performance. And we've got probably the most tortured network in the world because it's running these continuous performance tests. It's got all these stress tests going on at the same time. And that network had all kinds of interesting packet loss issues, all kinds of network driver bugs that were exposed. And it's because that network is unlike any other network in the world that you have to actually test it on every single deployment that you go out there to make sure that what you've assumed about reality is actually true. So the other thing about performance is that no one seems to agree on what performance is. I asked a bunch of people, what is performance to you? And I got like 20 different answers. I picked, this is my Skittle slide. Here's the rainbow of performance options that I got. And so I kind of categorized what performance looked like for individuals. So I picked two axes here. There's a throughput cost axis. So there's a measure of, is this performance in terms of making things cheap? Or is this performance in terms of getting lots and lots of things done? And then I picked a client-server access. Is this something that I care about for client machines? Or is this something that I care about in the data center? And then I just started plotting. These are what, When I think about what reference set performance is, so the amount of memory that I'm using loading up my object code, well, I think it's kind of client, it's kind of in the cost axis. But individuals may disagree. So you see a little bit of movement on these dots as they matter to you. And you have to think about all these different types of performance, which is kind of a hard thing to keep in mind at the same time. And so what we like to do is categorize these different types of performance according to 3 basic kinds of resources. There's memory resources. This is the amount of storage space I have. And this could be, actual live RAM for memory. It could be disk space. It could be space on my SQL Server storage. This is my ability to retain information. And there's a bunch of different performance measures related to memory resources. So you've got reference set and working set and thread count, the things that are actually going and executing in memory. I've got pool sizes, caches, buffers, those types of things. I've got just the overall capacity of my system. How many instances can I load? How many things can I store in my database? The next kind of performance measure that we've got are CPU resources. This is my ability to process, to think, to do actions. And again, it's not always going to be limited to CPUs on my desktop. It's sometimes the ability to go into the cloud and talk about performance of distributed resources up there. And so I've got a number of different CPU measures. So I've got the startup time of my system, both cold start, warm start. I've got my utilization. How efficiently am I using the CPU throughout the day? And then I've got measures of things like concurrency. I have 20 tasks. Can I execute 2 of those tasks at once? Can I execute 20 of those tasks at once? So concurrency is a vital measure in terms of interacting with the performance of other systems. Finally, I've got I/O resources. This is my ability to communicate, my ability to express myself to the world and interact with other parties. So I/O resources are typically what we think of as being extremely performance limited in many systems we deployed classically. As the topology of your networks change, as you move to different data center environments, as you go up to the scale of the web, the performance differences are going to change in each of those tiers. And so while we saw a lot of I/O restrictions before, when I had a client-server system, a single server sitting there, and many, many clients attacking it, all sending their requests at once, when I think about bigger distributed systems where I have data centers all over the world, I/O actually starts being a little bit less of a difference, except for this one bucket in the corner, which is coordination. There's a certain amount of overhead that I have in order to interact and coordinate state between systems. So if I have a distributed service, and I have some state that multiple pieces of the service know about, I need from time to time to have everyone agree on what that state is. And a classic example of coordination performance that you might not expect is from Amazon's cloud service. So if a couple of months ago, Amazon's cloud went down for a couple hours. And what actually happened is that Amazon has 2 different kinds of tasks. They've got coordination tasks, where all the servers try to agree on what the state is, and they've got application tasks. And a little bit of state corruption got introduced into the system. And so all these coordination tasks, which were higher priority than the application tasks, tried to figure out what was going on. And so they start sending each other messages. And the corruption spread a little bit farther and a little bit farther, and now you got more and more of the systems spending their time coordinating. And eventually what happened was that all the processor time of the entire Amazon cloud got spent doing coordination as opposed to actual application work, and they had to take the server down in order to flush out all the bad state in the system and bring it back up. And so that was an example of how bad can coordination performance get? Well, it can go to 100% of your CPU time. And it's always a matter of controlling the amount of time that you spend doing kind of this non-productive work versus your productive application work. So the next lesson I want to tell you about, and this is really the most important part of the talk. So if you take nothing else out of the talk, take this one lesson home. When I talked to the engine mechanic, he wasn't just knowledgeable about how the engines worked. He knew all the depths of the principles of physics, about combustion, compression. You could explain why things happened in the engine like they did. And I thought about what we've done in WCF, and we've never told you why WCF works like it does. So I sat down. What is the principle behind WCF that can simply be used to communicate and understand how the system works? And I came up with this principle I call the push-pull principle. There's 2 ways that data can be exchanged in the world between parties. I may have some data, and I want to send it out to you. So I can say, well, I don't know if you want this data, but I'll just push it in your direction. And that's the push model. And you see that in things like HTTP, TCP. When I want to go to a website, I don't wait for them to solicit my HTTP request, I just go up to the web server, start sending some HTTP data. And maybe they'll process it, maybe they won't. The second kind of interaction between parties is pool. So I don't have any data, but I want some. So someone out there has got some data, or at least I think they do. And I'll ask them from time to time, can you give me data? So there's push and there's pull. And then the entire world gets categorized in terms of those two models. And when I have components that are lined up together, push to push, pull to pull, everything is great in the world. Whenever I want to invert the direction of exchange, something very interesting happens. In order to change those arrows around, I need some kind of control mechanism. When I've got someone pushing data in and someone else pulling data out, I need a buffer to mediate that exchange so that data that gets pushed in isn't lost in the meantime. If I've got the opposite, I've got someone that's expecting you to pull and the next person's expecting you to push, if I just put those two components together, nothing's going to happen. The system isn't going to run because both of them expect the other person to be the active party. So I have to have a pump running there continuously, pulling from one side and pushing to the other side. And whenever we introduce one of these control mechanisms, a buffer or a pump, that's where a knob appears. So when you think about every single setting in WCF, every time you see a control knob, a quota, a throttle, it's because one of these buffers or pumps happened. And so just by thinking about how the system is arranged, you can figure out where every single knob is going to appear. And by thinking about what resources are going through that particular exchange, you can figure out what those knobs are protecting. And to show you that's true, let me give you some examples. Here's a look at WCF, simplified just down to the level of push and pull. And I have taken a look through it in terms of control and in terms of data. So let's think about WCF control flow. I'm going to have someone sending me messages on the network. And they're just going to push that data at me for the typical transports that use in WCF today, so like HTTP and TCP. And then I've got transports pooling that data. So if you know how channels work, if you've seen the iChannel interface, I'm going to have a certain shape to my channel. It'll be iInput channel, iRequest channel, iDuplex channel, but they'll all share a common method. It'll look like a method called request, and it will take as its argument a timeout. That's just how long I'm going to sit there trying to pull data before I give up. So you know it's a pull model. To contrast that, if you look at how the ASP.NET pipeline model works, there's an interface called iHTTP handler. And on that interface, there's a single method called process request. And the argument to process request is actual request data. ASP.NET works by pushing data at you. And that mismatch, actually, between push and pull is why WCF slows down if you put it in ASP.NET. So when I turn on ASP.NET integration, I have to convert between the push and the pull between ASP.NET and WCF. So what actually happens there is we're going to burn a lot of threads pulling that data up so that we can put the buffer in between. And we did a fix in .NET 3.5 SP1, which was to enable asynchronous HTTP handlers. And that actually took away a lot of the performance difference between WCF hosted outside of IIS and WCF hosted inside IIS, because we could solve that push-pull problem by using an asynchronous programming model to mitigate the fact that we needed a buffer there. Back to WCF. So as data, or as connections are coming out of my channels, so I've accepted some connections coming from the network, I then have to go and figure out what I'm going to do with these connections. And that's the dispatch step. Here's the biggest pump in WCF. And because system service model is, I think, the biggest DLL in the .NET framework, this is probably the biggest pump anywhere. So we're going to sit in a loop, and we'll see this loop in detail in a minute. We're going to pull connections out of the channels, and we're going to figure out where those connections should go. We're going to figure out what instance they should go to. We're going to figure out what operations we should invoke. But again, I'm going to have a pump running continuously, pulling from the channel side and pushing to the dispatch side. And in my application, if I write my typical service operations, where I take type parameters on all my methods, that is just another example of push. A method call is a great example of a push communication. So from these 5 arrows, which I've used to describe WCF, there's a single word on each arrow. This is less about WCF than probably any single piece of documentation you have. But you can figure out where exactly every single quota is in terms of control, just by looking at these arrows and thinking about what resources are involved. So when I think about the mismatch between network and transport, I know I'm going to see a lot of buffers down there. I'm going to use TCP as my example here, I'm going to see buffers, for the number of connections, the number of listeners, the number of accepts that I've got going. When I think about the mismatch in direction between the channels and the dispatcher, I know there's a pump there, so I'm going to have all kinds of control flow knobs, max concurrent calls, max concurrent instances, max concurrent sessions, to control how fast the pump runs. The same thing is true for data. So now instead of thinking about connections, let's think about the actual bytes that are flowing through. So again, I'm going to have the network just pushing bytes at me. I'm going to have the channels that are pulling bytes. But now if you think about how the message encoder interfaces work, when I'm transferring buffered data, I'm going to have a method, read message, write message, that takes an array segment. And so I know that I have to have buffered all the data in order to run this encoder. And while we haven't told you how any of our transports work internally, just from the fact that we have these two opposing arrows, you know there has to be a pump somewhere in those transports. And there is a pump if you go and look through it. That's the pump that does message framing. Whether it's the message framing in TCP or the message framing in part of the HTTP protocol, there has to be a pump there. And so that pump must be inducing knobs. Again, as we go up, messages come out of the encoder. They go through the rest of the channel stack. So there's a little bit of mismatch there. So we'll see how that works. And the channels, well, they're going to take the data out of there, get pulled through, again, by the dispatch. They'll go through serialization. And serialization has to pull all the data out of the message in order to get your type parameters, convert it to C# objects. Again, we're going to push at your application. So just from those 6 arrows, we can infer exactly where every single control knob in WCF is. So when I think about what's on my network transports, I'm going to see control knobs for adjusting the buffer sizes, for controlling kernel buffers for my connections. When I go up to the encoder, I'm again going to see the buffer sizes that are going to be used as part of that pump implementation. I'm going to see, when I look at the message objects, the quotas that are going to be involved in terms of copying those messages around. And if you've ever wondered what all those XML dictionary reader quotas are in Service Config Editor, well, it's because we have this mismatch between channels and serializers in terms of push-pull. So the serializer needs to run at a pump, and so it needs to limit the number of max, it's going to have max items in object graph, max array length, all those types of limits on there. So just by looking at the push-pull diagrams, we can figure out where all the knobs are and how they work, regardless of what you actually get told about the state of the system. So you find internal details that we never talked about before, just by thinking about going through this. And so you may ask to yourself, we recommend that you use stream transfers whenever you have large messages. Why? Well, what happens when I do stream transfers? Well, I turn my app around. Instead of having typed arguments pushed at me, I'm going to get a stream handle. I'm going to pull data out of that. So that data is going to get pulled through the serializer and pulled through the channels. And so by turning everything around, we've now aligned it. Pull, 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 pull. We've gotten rid of those pumps and buffers that are touching all my data. So why is it faster to use stream messages? Great. You can figure it out just by looking, pumps and buffers disappeared. Of course, this isn't perfectly true, because for small messages, I can take the performance hit of spending some memory on those buffers, and so I'll get a little bit of read ahead. Because this is the pull model is only going to work when I actively pull. When I actually get the read ahead of pushing, then I can sometimes get a little bit ahead of where the application is and use that as a way to process messages faster. So that's why there's that division between large messages and small messages. Of course, whenever I tell you something, there's always going to be exceptions to the rules. And kind of the way I think about it is, you don't let the facts get in the way of the truth. The truth is the push-pull model. And that's the way to think about everything in WCF in terms of how, when I adjust those knobs, it's going to affect my application. Some counterexamples of those you're going to find. So I told you every single channel is going to pull. It turns out some of the channels push. And that's because those channels need to do work even when the application isn't. And the two canonical examples of those are reliable messaging and one-way channels. So the reliable messaging channel needs to be able to retransmit requests as many times as necessary in order to get it from one side to another. So we know just from the fact that it works in terms of that push that there has to be all kinds of buffers and pumps. In fact, the reliable messaging channel is the most complicated channel in the system. And it has all those buffers and pumps we can infer just from the fact that we drew 3 arrows. Same thing is true for the one-way channel. When I get requests in, I want them to be acknowledged immediately when I'm using one-way messaging. So we know there has to be some kind of pump running continuously, pulling in all the requests doing the acknowledgments, and buffering the messages until I actually pull them. So if you look, what are the channels that actually have funny knobs on them that other channels don't? It's these two channels. And you can think about, what are the resources involved? Well, we have connections, we have buffers, we have messages, and we can figure out from those exactly what the knobs are. And it turns out those are the knobs on the channels. Same thing is going to be true down at the network. I told you every single network is going to push. Turns out some of the networks are going to pull. And in fact, even for the networks that push, sometimes they both push and pull. So TCP, HTTP, those types of connected systems typically are going to push. Queues are going to pull. But even for TCP, for instance, it's not a pure push. I'm going to send, and eventually the network is going to back up between the two parties. And so I'm going to have this flow control pushing against me, telling me to send slower. So if you look at how TCP works under the covers, it's got this sliding window. That's our buffer. So I'm going to fill up the sliding window by send. Eventually the buffer is going to get full. And then I've got this pump on the other side. And I know a pump has to exist because I changed the arrows and then I had to change it back. So that pump is what's going to control when we start resending. So you'll see down in the Windows 32 registry controlling TCP sys, all kinds of control knobs for buffers and pumps that are implicit in the TCP protocol. So this is a principle that you can take not just from WCF, but apply it to other distributed systems as well. And when I think about how my WCF service talks to other parties, I can think about what they're doing in terms of push and pull and modulate how my WCF service is working in order to align with what they're doing. So I can think about, if I've got someone that is pulling data from me, if I turn my WCF service around from going from push to pull, aligning better with the service that is consuming my data, then I'll actually avoid buffering or pumps in terms of data transmission and make my overall distributed system faster. So I promised you a deep dive. And I told you that the WCF pump was probably the most complicated pump in the world. So let's see if we can learn how the WCF pump works in the next 10 minutes. So we know that there has to be some pump running there because we had push and pull out of alignment. And we knew that there were some knobs. But we don't know how those knobs actually affect the resources until we look at code. And parts of that framework are released where you can just look at the source code. So the system NCL libraries, for instance, you can go get all their code. WCF is not under that program yet, but you have a tool called Reflector. You may find that there is actually source code sitting on your system. It's just not source code in text, it's source code in IO. And if you went and actually tackled through here, you could figure out exactly how the pump worked and figure out how all the knobs worked. But I'll save you the trouble because you came to PDC. So here's my service to you, telling you how the WCF dispatcher actually works and what those knobs are going to do. So I'm going to sit in a loop, and I'm going to continuously accept channels. So I've got a channel listener that I've opened up for my binding, and from time to time, people will connect to me. And remember that max concurrent sessions knob? We're going to have an acquire session throttle that's going to count against those session throttles every time I go through this loop and accept a channel. So if I'm using a sessionful transport like TCP, this will be the knob that actually controls how fast I'm going to accept connections into my system. For datagram channels like HTTP, we'll only ever get one of those channels because all those HTTP requests look like any other. And so this knob won't actually have very much effect at all. So it depends on the actual types of channels I have for how fast I go around this loop. Every time I get one of these channels, I'll kick off a message pump. And we'll look at the message pump right after this. When I'm done with the channel, I'll close it, release the throttle. So that's how the cycle works, continuously pumping. I've shown you this synchronously. There's actually all kinds of asynchronous goo going around. Turns out, again, don't let the facts get in the way of the truth. If you think about how an asynchronous process works in a purely synchronous fashion, you can typically get 90% of what you need to know about performance just from that level of thought. So let's look at the message pump. I've got one of these channels. I'm going to sit in a loop. Again, I'm going to receive messages on them. And this time, I'll acquire the other two throttles. I'll get my instance throttle and my call throttle. And an interesting thing is going to happen here. So if I keep going around this loop, I'll select an operation. I'll dispatch a request. Getting into the dispatch request in a second, because that's probably the interesting one to you. And when I'm done, I'll release the throttles. What does that mean, though, release the throttles and acquire the throttles? If I have a session-full channel, I'll actually only release the call throttle. I'll hold on to the instance throttle every time around. And that will have an interesting performance implication. Because now I'm going to bias towards pumping messages on existing sessions because of the fact that I've held this throttle. So let's think about how that actually impacts your application. If I have a service contract that uses sessions, and some of those sessions are short-lived because I've got an operation that'll do a couple messages and it'll finish, and then some of those sessions are really long-lived. I'm going to continually exchange messages for an hour. Then if I'm actually running up against my maximum number of throttles, over time, I'm going to build up more and more of these long-running sessions. And if I hit my throttle limit, I'm going to start starving out all my short-lived sessions. So what this tells you, just by the way the pump works, is that I want to factor my service contracts so that I have similar lifetimes between all the different uses of the operations. So I want to keep the things that are long-running together with other things that are long-running, keep things that are short-running together with other things that are short-running. But I promised you dispatch request. And here is the point where if you're actually following through the code and you've managed to make it so far, this is the point where everyone gets lost. There's a reason for that. I've only shown you the boxes that actually matter for performance. There's actually 60 or 70 boxes in this diagram. And we actually found out a couple of months ago that we needed to know exactly what order everything happened in the dispatcher. It turned out no one at Microsoft knew how the dispatcher worked in exact order. So we sat down and cranked it through a piece of paper. And before this talk, 2 people knew how the dispatcher worked. Now there's about 502 people that know how the dispatcher works. But you're not going to get the details of every box. And so the promise I'm going to give you is if you want to talk about any single one of these boxes, come up after this session, and I'll tell you more. And we'll see exactly how much I know about the WCF dispatcher. But what are you going to do if you're going to actually try to solve a performance problem, and you get into this situation where there's just 50 different things that are going on, and you need to figure out what is the thing that is actually impacting my application? Well, you start by a process of elimination. You don't need to keep everything in your head at once. So I go through here and go, well, authorization. Authorization might take a while, but I know that my validator is really fast. I see performance problems even when things are running good and everyone's validated. So authorization is probably not a factor. Create instance context, create instance. Well, I've got this instance, my max can create instances, and I'm not really pushing up against it. So while creating an instance is going to cost me some amount of memory, some amount of CPU time, maybe that's not the cause of my performance problem either. So for a typical application, you'll go through and you'll start crossing out the things that don't matter for you. And I've picked out kind of the 4 that matter most in the general case. So what you'll see is that there's a couple of pieces where we actually do serialization of requests onto a single thread. So one case of that is going to be when we lock the instance context. If you've seen the knob for concurrency mode multiple versus single, here's where we'll actually block if you put concurrency mode single in there. Bind to thread. If you remember the feature for synchronization context introduced in .NET 2.0, when I think about how a WinForms application works, I've got this special UI thread, and I can only do operations when I'm on the UI thread. Think about how ASP.NET application works. I've got these special worker process threads, and so ASP.NET has a certain threading model I need to follow. Bind to thread is where we actually get you on the right thread. And bind to thread is interesting because this is where we have the first opportunity to start pulling the next message. So first 6 boxes in there, they're all going to go executing one by one, and we're not going to go and kick off the next async request until we bind to the correct thread. So what does that mean? Well, we saw some boxes before there. We saw authorization, we saw message inspectors, and we've actually seen in real applications where people come to us. They say, I bought this $20,000 computer. I've got 20 requests that are getting processed per second. What's going on? And we trace through there and we figure out, well, okay, your authorization module, that was doing a database lookup, and that was taking 50 milliseconds. Well, okay, you got 20 requests per second because you spent 50 milliseconds there, and we can only turn over 1 throttle at a time because you blocked our ability to go async. Message inspectors is another common one. We see message inspectors that run and run and run, and when you do all the work in the message inspector, you're going to lose the concurrency of WCF. So again, understanding how this process works is a key way to improve your application performance. The last 2, serialization and invoking the operation, those are the 2 things that should be the most expensive thing in your system. Serialization is where I'm going to actually touch all my data. Invoking the operation is where I'm going to actually do all my business logic. So typically, I'm either going to have really expensive data or really expensive logic, and I should see all my CPU time. And for most services, I should see 100% CPU utilization running all the time, where I'm not using my machines very effectively. But I should see all my time spent in those 2 boxes. So let's sum up the WCF today. Gave you a bunch of different lessons. So performance, please have performance. We recommend it highly. It will help your application. Second, understand how the system works. You don't have to keep everything in your head at once, but you have to understand all the different pieces and how they interact. Third, first principles are tremendously useful, more so than you might imagine. By going through this first principle look, actually figuring out this push-pull principle, we didn't know this push-pull principle before we started. Just sat down, thought about it for a couple days, and prepped for this talk, and figured out there was a way to explain WCF where it actually made sense for people that had worked on the product for years and didn't know what all these knobs meant. Showing them this principle actually clarified, and in their minds, they learned more about how WCF worked. And finally, know when you're done. Take some assumptions, make a hypothesis, do some tests, and go around and around this process until you hit your performance targets. When you hit the targets, stop. Because every time you do a performance optimization, every time you turn one of these knobs, add a new trick in, you're going to degrade some other part of your system. You're going to make the code more complex. You're going to spend more programmer hours. And so I like to say the performance curve degrades on the high end. If you push the system too far in terms of tuning, you're going to hurt yourself in other ways. So that was WCF today. Where is WCF going in the future? And here's where I want to tell my second story. This is a story about Starbucks. I know people have told stories about Starbucks and distributed systems before, but this is my Starbucks story. So Microsoft is located kind of in a suburb of Seattle. And so sometimes I go downtown to Seattle, and there's this place called Pike's Place Market. It's this big, famous market. You get millions and millions of people going through here. And it's really eclectic. So you might see, this little Mexican grocery store next door to the high-end wine shop that sells $1,000 bottles of wine. It doesn't make any sense how the stores are arranged. And if you look up and down the street, you don't see a single commercial establishment. There's no McDonald's. There's no anything like that just along this Pike Street. But then right in the middle, there's a Starbucks store. It's the only recognizable sign that you'll see in either direction. And you're wondering, why is there a Starbucks store in the middle of this eclectic little shopping area? And if you go up to the front of the store, there's a plaque on the front. And it says, first Starbucks store, founded in 1971. It's the original store. At one point in time, Starbucks was an eclectic little coffee shop with one tiny store. Now they're the official coffee supplier of professional software conferences everywhere. And when you go in the store, because it's the only recognizable store and Starbucks is really famous, it's packed with people. Forget the size of this room. The Starbucks store is not much bigger than the stage. And you go in there, and there's like 50, 100 people all trying to get coffee. So Starbucks has, in this store, probably the biggest performance problem I've ever seen. And what they've done is something really creative. You go in, they've got a little room area for cashiers, and they've got a little area for baristas. But because of the way the store is arranged, it's long and skinny, they can't put the cashiers next to the baristas. So the first time I went in there, I went up to the cashier, they took my order, and when you go to Starbucks, they write your name on the cup, they write your order down. And so the cashier put the cup down. Then they took the next order, go put the cup down. And I'm wondering, what's going on? How am I going to get my coffee? Are they going to carry these things back and forth? Eventually, the cashier stacked a bunch of cups up. And the cashier caught the attention of the barista over there. Kirill's going to be my barista. And what they did, and this was kind of surprising, is, the cashier just kind of took the cups and threw them over to the barista. And as the cups were sailing overhead, I had a realization about performance. Starbucks solved their performance problem by being extraordinarily asynchronous. There's no coordination of when you come in and go to a cashier. There's no coordination between the cashiers and the baristas. You don't take the time to carefully carry the cups from one side to another. So let me tell you how the Starbucks story applies to WCF 4.0. So I've given you a little bit of visualization. Here's kind of a floor plan picture. I walk in, there's a bunch of customers going in, cashiers on the side, baristas back in the corner. And I told you about a process they use for making coffee. So everyone's going to line up. They're going to go to a cashier, place their order. Eventually, the cashier is going to throw the cup across the store. Baristas will mix the drink, and it'll serve it to you. And this doesn't look much like a typical distributed service, because I've drawn it in terms of a floor plan. But what if I drew the same service like this? Do you recognize this service? I've got a customer tier. Those are all the people on my internet. I've got a cashier tier. This is my middle tier of services. And I've got a barista tier. That's my back-end tier of services. Typically, you have databases rather than coffee, but for this example, it'll have to do. And when I go through my coffee service, I'm going to have Customers come up. They're going to send messages to the cashier in order to place an order. All those messages will go into a queue. Cashier is going to eventually send a bunch of orders over to the baristas. In between, the cashier will mark a correlation address on my cup so I can actually find my order at the end of the day. But again, it'll go through a queue, so that they're decoupled between the middle tier and the back end. And then when my coffee's ready, the barista is going to contact me. It's going to send a message back, which has my coffee in it. And then again, that'll go through a queue. They just put the coffee on the counter. They don't find me in the store and hand it to me. You can build this service today using WCF, but writing a whole lot of code. So how are we going to change that? Let's go through some pieces. First of all, you'll notice that the cashiers all work the same. Doesn't matter which cashier I go up to. Same thing with the baristas. And so what they're really doing is that I've got a queue. And I've got a bunch of competing consumers on those queues. And my cashiers are scaled out across all those competing consumers. When I told you about Dublin, Dublin is extensions to the Windows Application Server role. And it's also a bit of an extension to WAS, the Activation Services in IIS. So Dublin is going to include tools, management, administration, scale out, all the things that I need in order to effectively run multiple copies of my service and make that kind of service architecture easier to build. You see a lot of queues in this picture. In the box, we shipped MSMQ in WCF 3.0 and 3.5, and that was it. We're putting a lot more of an investment into queues as we go forward. We're going to introduce a new queuing model. So transactional queues were what you had before. If you didn't like your message, your business logic blew up, the message went back in the queue because all my receives were done transactionally. What we're going to introduce is a second queuing model where I take a cheap lock against the messages, leaving the message in the queue. And I can have all my competing consumers take locks in their messages so that other people can't grab them. And then those competing consumers can take as many transactions as they want. So we've nested transactions inside of these locks to give you a nested transaction semantic. So we've decoupled the receive from your actual business processing. We're also going to put a second queue in the box. So MSMQ supports the transactional model. It will support the new peek and lock model. We realize that there is a whole lot of deployed infrastructure out there in the world already. And Microsoft is making a big commitment to interoperability with other parties. And in particular, for financial services, business-to-business integration, you see a lot of IBM's MQ series product. So we're going to put a channel in the box for IBM MQ series as a second queue. Third piece. Remember that cup throwing? Well, sometimes those cups don't get there. You know, they hit the ceiling, the barista drops them. I don't want to roll back all those operations. You know, I don't want to pick the cup up, erase my name off of it, get my money back, go to the back of the line, because that's what a transaction would do when it rolls back. It encounters a failure and undoes all the work. Instead, what I want to do is take some compensating action. Make it up to you. So what I'm going to do is write a new cup. You don't have to pay me money again. You don't have to go through the line again. I'll just fix up the fact that I dropped the cups and try it again. So we're introducing into workflow a new compensation model for describing compensatory actions and the triggers for when those actions actually get executed. Finally, you'll notice that there's a bit of correlation going on here. If you think about how correlation worked in WCF 3.0, we had one option, which is correlation based on a network resource. So you had callback contracts. 3.5, we introduced a second kind of correlation. So there's the context exchange. Worked a lot like HTTP cookies, but over SOAP protocols. Downsides of context exchange were that you had to change your messages. You had to use request reply in order to make use of it. In WCF 4.0, you'll see a wide variety of additional correlation mechanisms. You'll have a general purpose framework for correlating based on the message body, the message headers, other content. We'll introduce new protocols for correlating on addresses. In general, making the entire correlation story better. Ed Pinto will tell you more. So if you go to the WCF WF talk, correlation will be prominently featured. And with that, what we're going to do is I'm going to offer you a deal. These sessions are short because it's a 45-minute lunch session. You don't have much time for questions. So we're going to take as many questions as we can until we get kicked out. Then I'll spend the next 2 hours down in the WCF lounge. Any performance question that you want to ask, come and talk to me. Look for anybody that's wearing one of these WCF badges. They're black and purple. If you have trouble finding the WCF lounge, have someone direct you to the giant 20-foot balloon that says WCF on it. So we'll take questions, come down the microphones, and for people that aren't here to ask questions, fill out your evaluations. Thank you. Left here?
Hi. Any suggestion about connection pooling in WCF?
So you had a quick connection pooling? Can you
I would like
more?
to be able to make a better job with connection pooling in WCF.
Okay, so there's a couple of things that we're introducing in terms of making more efficient use of connections, reusing proxies, reusing channel factories. So you'll see some of those optimizations already went into 3.5 SP1, where we made channel factory a little bit faster. We're doing continual types of optimizations like that, giving you better connection pooling just out of the box, so you don't have to do any work for that. And we'll also expose some of the connection pooling that we got internally. Thanks. Question over on the right.
Yeah, hi. Do you say you're having a channel for IBM MQ
So the question was, do we have a channel for IBM MQ? And the answer is yes.
with 4.0 release?
So it will be undetermined how it ships so far.
Is this the same channel that IBM is currently writing that's in alpha?
So the question there was, how does this relate to the AlphaWorks IBM MQ series channel? And this is our own implementation. So this is actually taking advantage of all the new WCF 4.0 features for the Q model. The channel that the IBM wrote doesn't do that because they haven't seen our Q model yet. But we are expanding and working with our IBM partnership to make sure that we have the right MQ series channel.
Got it. Okay, thanks.